Hey Cougars, it's Mr. Franklin, and it has been a while since we've done some video notes. So just remember, I'm going to run through this fairly quickly. If you need to pause it, please pause, write things down into your notes packet, and hit play when you're ready to continue. I will also try to link some other lessons I've taught on momentum if you want to learn more about it. So for our notes, lesson 4.5, conservation of momentum. Our learning intention is I can use conservation of momentum to understand a system of events before, during, and after a collision. You'll know you can do this when you can determine the individual and total momentum values before and after a collision. I can use conservation of momentum to predict the outcomes of various types of collisions, and I can identify conditions that mean momentum is not conserved. So let's just do a quick review of some of our vocabulary. So the first one is momentum is mass times velocity. The units for momentum are, what are they? kg times m per s, kilograms meters per second. What do we know about the momentum of a stationary object? If it's stationary and it's not moving, its velocity is 0, so its momentum is 0. Why will a semi-truck have a larger momentum than a car if they're both traveling at the same velocity? Because the truck has a larger mass. The car has a mass of 1,000 kilograms and is traveling at 10 meters per second. What is its momentum? It's going to be 1,000 times 10, which is 10,000 kilograms meters per second. And the car with mass 1,000 kilograms has a momentum of 20,000 kilograms meters per second. How fast is it traveling? So 20,000 divided by 1,000 is 20 meters per second. Okay, so that's a real quick crash course review of what we've done so far. So now let's look at momentum as a vector. So velocity is a vector. What does that mean? So a vector, we use letter V, has magnitude. So we have the size of the vector, and it points. The letter V points, so it has direction. So vectors have magnitude and they have direction. So that's a vector. Velocity is a vector. If we're going that way with our velocity, that's different than going that way with our velocity, or going that way, or going that way. When you multiply a scalar, which is mass, times a vector, you still get a vector as a result, okay? And so bottom line is momentum is a vector. So think about it. We have two penguins who have the same mass traveling at the same speed in different directions. Why is their momentum not the same? Because we're interested in the motion of that object and how it's traveling. If it's going that way, that is not the same as going that way. So there you go, if you need to copy that down. Okay, conservation of momentum. Conservation of momentum in a closed system. Total momentum before is equal to the total momentum after the event. We've already kind of talked about this in my class. You can also think of it as the total momentum is the same before and after a collision. So we could say equal because we're doing math, but it literally is, they're the same thing. They're the same number, the same value. Everything has to add up. So really what's important is understanding the difference between a system. So when we talk about this, what actually makes up the system? So a closed system is something that's not affected by outside forces, but it could also be outside masses, outside things. We're only concerned with a certain set of objects, and only those objects are allowed to interact, and only the forces involved are the forces involved. Okay, so we're going to ignore a lot of friction. We're going to ignore all kinds of stuff. Okay, so if a car hits a brick wall, this is our example here. Car hits a brick wall. If the brick wall was standing on an ice rink, then momentum would be conserved. If the brick wall was made but just sitting on the ice, it wasn't like attached to the ground. If the car hit the wall, we would get a reaction to that collision, and the wall would probably slide on the ice just like the car would. Okay, That's what we're trying to say, is the brick wall isn't attached to something else, because once it's attached to the ground, now you have outside forces like the ground and some other things affecting the collision. So if it's attached to the ground, this means that we have the earth as well as the car and the brick and the wall. So there are external forces involved. So we have to be really careful about this, where what we see, we might go, why is it not working the way I expected? Well, that's partly because of outside forces involved. So let's kind of break it down into two objects colliding. So when two objects are coming from opposite directions, that means one has a positive momentum, so positive. One has a negative momentum. When the objects collide, these negative and positive momenta work to cancel each other out. So for example, 10 kilograms going 10 meters per second to the right. We have 10 kilograms, negative 10 meters per second going to the left. So the momentum here is 100 kg per s. The momentum here is negative 100 kg per s. The total momentum is equal to 0, because we add them up to find the total, and they cancel each other out. So this is before they collide. Now, when they collide, guess what's going to happen? After the collision, they're going to actually stop moving, because the total momentum is 0. So let me just show you. So we've got a mass here of 1 kilogram. We have a mass here of 1 kilogram. We got one going 5 meters per second to the right. We got one going negative 5 meters per second to the left. And we got an elastic collision. If I hit start, when they collide, they bounce off of each other. Okay. I can do inelastic. They can collide, and they're going to perfectly stick together. In both cases, the momentum before is equal to 0, okay? And the momentum after is equal to 0. Okay, so now I can do, let's do one that's stationary. So let's do one that's stationary. Okay, so this one's going to move, this one's going to be still. So here we go, we're going to play. Got 5 meters per second, they collide, and they're going to switch places. Okay, now if that's inelastic, you might get something like this. So very different reactions to different things, and it has to do with the stickiness and how the objects react with each other. But the most important thing is the momentum before has to equal the total momentum afterwards. Okay, so that's what we're getting to. And so just bear with us and always keep that in mind. So there's different types of things and how things interact, so you can get different results. So let's look at if one of them is stationary. We showed that it can swap, okay, velocities, but we can also have them stick together and both velocities will change. So there's a couple of different ways to look at this, okay? But the momentum before was 100 kilograms meters per second, because the object on the left was moving, object on the right was not. After the collision, the object on both objects might be sticking together and moving together. I mean, 5 meters per second, okay? It's not 5 plus 5, they're both moving at 5 meters per second. So 5 times 10 and 5 times 10, you add them together, it still equals 100, which is what we had before. Okay. So if two objects are stationary before something happens, we would call this an explosion, okay? So the total momentum before is 0, okay? When we say collision, basically an event is going to happen that creates impulse. And now they're going to explode apart, and we're going to get this. So this might look like this. If we had our simulation, we can set an explosion. Okay, so they're stationary beforehand, 0 and 0, and we hit start, and boom. Okay, so we had negative 10 going that way, positive 10 that way. The momentums are going to cancel out. It's still equal to 0. Okay, so before and after have to equal. So conservation of momentum means that, total momentum before an event is equal to total momentum after the event. So when does this conservation stuff break down? When the event does not occur in a closed system. There are other forces acting. So friction, which is always acting in the real world, mostly, okay? Or things like that, okay? So two ice skaters are stationary before they push apart. What will their total momentum be after they push apart? The same. So if they're stationary beforehand, their total momentum is 0. So guess what it is after they push? Still going to be 0. It's just one's going to go positive and one's going to go negative, and it's going to cancel each other out. If you add them together, it's going to still equal 0. Okay. Two cars with the same mass are traveling at the same speed in opposite directions. The momentum of the first car is 30,000 kilograms meters per second. What will the momentum of the second car be? So same speed, same car, same mass, but in opposite directions. So negatives is how we tell direction. So negative 30,000 kilograms meters per second. Okay. All right. So practice 1. A person is standing still on a skateboard. When they jump forward on the skate, use conservation momentum to describe what the skateboard must do. So if I'm on a skateboard and I jump forward, what's the skateboard going to do? It's going to go backwards because my momentum before was 0. So it has to stay 0. So when I jump forward, okay, I now have momentum going this way. That means the skateboard has to have momentum going that way. Okay. Okay. So we also have this one, this football analogy. A 100-kilogram offensive lineman going 1.5 meters per second collides with a 110-kilogram defensive lineman going -1 meters per second. Do they come to a stop when they collide? How do you know? Okay. So do their momentums cancel out? No. So it's 150 kgm per s and -110. There's definitely not going to be a coming to a stop in a traditional sense. There's going to be some motion going one way or the other. Okay. So what's really helpful if you get confused with this is you can also draw your picture, draw your before, draw your after, keep your two objects separate. That can be very helpful. Okay. So number 3, a ball initially rolling at 3 meters per second collides with the second ball, which is the following possible velocity for the first ball after the collision. Why? Oh, for the first ball. Okay. It cannot remain 3 because it's going to give some of its momentum to the other ball. Okay, so keep in mind, we're talking about the first ball. I had to think for a second because I was going, wait, is that the second one or the first one? It's the first one. So the first ball is coming 3 meters per second. It collides with another one. Even if they both keep moving afterwards, the one that started with 3 cannot keep the 3. Some of it has to be given to the other object, okay? In order for momentum to be conserved. If momentum is conserved, number 4. Momentum is conserved, how is it possible that a book sliding across the table slows down, thus losing momentum? It's called friction, okay? It's an outside force. So that's a crash course. Please, if you're lost, make sure that you're taking notes of your points of confusion. So when I come back to class, we can go over these things. But you should be able to at least keep in mind before equals the during part, which is our impulse, and then equals the after part, which is our momentum. Okay. You can use conservation, this idea to predict what's going to happen in the future. And you can identify things where you're like, oh, wait, momentum is not going to be conserved because there's an external force like friction or other factors that are outside of the system. All right, that concludes the set of video notes. Do your best, and I will see you soon.